Welcome to my YouTube channel. In today's video, I'll be explaining the Goldbach conjecture proof to you. But before we look at the actual proof of the Goldbach conjecture, we need to look at a particular function that I came up with, which is generating all the prime numbers to infinity. Let us quickly, without wasting time, we look at how the prime numbers can be generated by the function that I created. And I need to tell you that the prime numbers in this case that we are going to be using in that particular functions, they have a relationship with the triangular numbers, which I'm calling the special triangular numbers. Now remember the set of triangular numbers. Those elements in the set of triangular numbers, I have categorized them into two groups. There is that particular group of triangular numbers that I'm using to calculate the prime numbers. I'm calling it VM, that is called special triangular numbers. While the other one which are members of triangular numbers and yet I'm not using them to calculate the prime numbers, I'm calling them non-special triangular numbers. Now the special triangular numbers are represented by VM, while the non-special triangular numbers are represented by M. Now remember, triangular numbers, which is Tn, is the sum of special triangular numbers plus non-special triangular numbers, which is equal to the union set of the two. Also take note that the special triangular numbers intersection non-special triangular numbers is an empty set. Now, how do we find the special triangular numbers from this set of triangular numbers? So special triangular numbers, which is VM, is equal to all triangular numbers minus non-special triangular numbers, which is equal to triangular numbers intersection non-special triangular numbers complement, where Tn stands for the formula for calculating the triangular numbers, where n is a member of natural numbers. Remember, the first number that we use, or integer, when calculating the triangular numbers is 0. But in my case, I've excluded 0. Now, how do we calculate M, non-special triangular numbers? We can calculate them by multiplying the odd numbers and the product squared minus 1 over 8. Now, these odd numbers, A and B, are greater than 1. Therefore, the formula for calculating all prime numbers is, so prime numbers, P, is equal to the square root of 8 times special triangular numbers Vm plus 1, where Vm is equal to T triangular numbers minus non-special triangular numbers, which is equivalent to triangular numbers intersection non-special triangular numbers complement. So now the set of non-special triangular numbers, I created a multiplicative table for them. And these odd numbers, they start from 3, 5, 7, 9, 11, going up to infinity. So the table that you are going to see, it's not they are representing all the non-special triangular numbers. It's just a portion, a small part of non-special triangular numbers you should take note of. So here we have a set of non-special triangular numbers. So this set is only catering for these elements inside. The outer part they are not part of non-special triangular numbers, but the inner part. So we call these elements or numbers in this table as non-special triangular numbers, and the table is called non-special triangular numbers multiplicative table. So these are the numbers that cannot be included as we calculate, which should be removed from the set of triangular numbers. And when we remove these numbers which are inside here, we remain with special triangular numbers that will generate prime numbers to infinity using my function. Important rules on the use of M and Vn. So on the use of M, which is special, non-special triangular numbers, and Vm, special triangular numbers, there are some rules that we should take note of. The first rule, make sure that the special triangular number input in my function is less than the non-special triangular number in the second row or column in the non-special triangular multiplicative table. In short, we are saying, let me use the table. You can see, so if you want to calculate the prime numbers, we need to be using this table for non-special triangular numbers. But we also need to know that the second row here, the number is 253. It can be above, it is above these. We are going to have numbers that are above 253. Remember, I just said this is just a portion of that. So we have a reflection here. The numbers will have right upper hand there, down also left hand there. They are just a reflection. So in my column, the largest, in my second column, the largest non-special triangular number is 253, while the other side in the row, the largest is 253. So as we are coming up with the special triangular numbers, we need to make sure that the largest special triangular number in the set of special triangular numbers must be less than that particular largest non-special triangular number in the last part of the second row or second column. We proceed to the next part. The other rule, in order to include a 2, the formula that I've given you, which is the square root of 8 times the special triangular numbers plus 1, excludes a 2 from the set of triangular numbers. So in order for us to include 2 to be among the prime numbers, deliberately we need to include 3 over 8, which is 0.375, deliberately. Otherwise, this is the only limit to my formula, because among the special triangular numbers, we have no number that can be put into the VM or substituted into VM to give us a 2. So deliberately, we use, we need to use the 0.375. If we use the 0.375, that means the 2 is now included. We go to the example. Example, find all the prime numbers using the set of triangular numbers below. So the set of triangular numbers that we have triangular numbers up to 190 from 1. Now, for us to find the prime numbers using the special triangular numbers from this set of triangular numbers, first we need to remove the non-special triangular numbers using the table. So let's see the solution. So using the table, you realize that 10, 28, 55, 78, 91, 136, 153, 190, they are part of the non-special triangular numbers. Let's check and see here. I quickly move you a bit behind. We see the set of non-special triangular numbers. You can see we have a 10, 28, 55, 78, we have 91, 136, 190. So these numbers are falling under the non-special triangular numbers. So these are the numbers that we have in set M. Now, we need to remove these numbers from the special triangle, from the triangular numbers, we subtract Tn minus m, and when that happens, we have Vm having these as elements remaining in that particular set for special triangular numbers. So we simply subtract. We are now going to insert in the formula. We shall be substituting our Vm in the formula in order, and the prime numbers that will be coming out, they are all in order. So we'll start with the smallest special triangular number. We substitute on Vm, goes to the next special triangular number, we substitute, we do the same. The numbers that we'll be getting are all prime numbers. So far I've tried so many prime, special triangular numbers, and the results are always prime. So let's see how these are the solutions. So we are using this formula as a function. Then in order to include 2 among the prime numbers, 0.375 must be included. So let's see, the first prime number P1, we substitute Vm with 0.375. We'll have that 4, then square root is 2. To get the next prime number, we get the first special triangular number from the set of triangular numbers, which is 1. Then when we do everything, we have 9, and the square root of that is 3. The next special triangular number is a 3. When substituted here, we have 25, and the final result is 5. So we can keep on doing that. All the numbers that will be coming out will be all prime numbers. We can see all 66 substituted gives us 23, 105 substituted gives us 29, 120 substituted gives us 37. So you can try as many special triangular numbers as possible to substitute them on Vm, and all the results will be prime numbers. So to try as many as possible, it means that the multiplicative table of non-special triangular numbers must be expanded, it must be increased. And don't forget, the largest member of the special triangular number must be less than the largest number in the second row or in the second column of non-special triangular numbers multiplicative table. We look at now the Goldbach conjecture. Now, what does the Goldbach conjecture state? This Goldbach conjecture, it's a conjecture that is almost now 300 years old. It hasn't been proven, and I believe the reason why it hasn't been proven, the mathematics community, none of them has, any mathematician has come up with a special formula that can generate all the prime numbers. Hence the reason I believe that the Goldbach conjecture cannot be proven. But looking at the formula that I've come up with, which is generating all the prime numbers, we are then able to prove the Goldbach conjecture. What does the Goldbach conjecture state, by the way? States that every even integer greater than 2 can be expressed as the sum of 2 prime numbers. Every even number greater than what? 2 can be expressed as a sum of 2 prime numbers. For instance, 4 is greater than 2. I can add 2 plus 2, which are all prime numbers, to get 4. I have 6, I can add 3 plus 3 to get 6. I have 8, I can add 3 plus 5, which are all primes, to get 8. To get 10, I can add 3 plus 7. I have 10 to get 12. I can also add 5 plus 7 to get 14. I can simply add 7 plus 7 or 11 plus 3. So assume these numbers, should I say this conjecture, numerically it has been proven to be true. Using millions of numbers, it holds true for all even numbers. Now, a formal proof has been elusive to the mathematicians. So, the Goldbach conjecture once more states that every even number greater than 2 can be expressed as the sum of two prime numbers. Now let's assume the two prime numbers is P1 and P2. Now when we add them, we need to get an even number. In this case, an even number is 2m, where m is greater or equal to 2. Now P1, P2 are members of, these are prime numbers which are members of the results that are obtained using my formula. Now for every special triangular number Vm, there exists a prime number Pn such that Pn is equal to square root of 8Vm plus 1, where Vm and V2 are members of special triangular numbers. Now let's look at this proof. By using P1 equals the square root of 8V1 plus 1 and P2 equal to 8V2, square root of 8V2 plus 1, where Vm is equal to Tn intersection m complement. Show that P, when we add the two prime numbers, they'll give us an even number, where m is greater than that. Now I'm going to use the left hand side to show that it reduces to the right hand side. Here we go. When two prime numbers are added, the result is an even number, which has been numerically proven using trillions of numbers. So here, what is our P1 and P2? So our P1 is 8 square root of that, 8V1 plus 1, and P2 is simply 8V2 plus 1, the square root of that. So it's equal to that. We move on. What happens next? We factorize the common factor in the first part, that is 4. The second part also, the common factor is 4. We factorize that. Then next, we find the square root of each independently, square root of 4, square root of the other part, just the same as the other next term. So what happens next? We find that the square root of 4 outside gives us a 2. Then we proceed, we factorize the 2, we end up having what is inside the square brackets there. We move on to the next part. We now find the square root of everything inside. But before that, I drive you a bit back. We need to simplify what we have inside here. Once we simplify what we have inside the square root, we are going to get what we are able to see on the screen there. Next, we are going to find the square root of the denominator and numerator independently. You can see square roots signs there independently, now working on the denominator and the numerators. So next, we know that square root of 4, it's 2, so we have 2 down there. So we look for the lowest common denominator, which is 2. We express what we have inside as a single fraction. So next, we have a single fraction inside. But remember what square root of 8V1 plus 1 and what is square root of 8V2 plus 1 means. The first one means the first prime number that we are adding. Then with the other one means the second prime number. So we take back P1 and the P2 into that. So substituting P1 and P2, we get this one. Now remember, we have 2 outside, we also have 2 the other side. So that simply means the P1 plus P2 divided by 2 is simply equal to m. So m is equal to what we have inside. If that is true, it means now that the proof has been given, or should I say we have proven the Goldbach conjecture. So look at this carefully wherever you are. Try to see and provide any counter example, more especially on the function that is providing or generating all prime numbers to infinity, except where we use 0.375 to include a 2. Thank you very much for watching, and you kindly share this video to many mathematics platforms. I'll be glad. Thank you very much.